So this talk is going to be on second order methods in bandits. This is a joint work with Praneeth, who is here, and my collaborators from Princeton, Jennifer and Milad Hazan. This work was published in Cold 2021 and 2024. But I would like to say, since we published this in 2021, there were a lot of works which try to build on top of this. I'm not going to cover that, but it's mostly our version of the second order methods. Okay, so just to set up the problem formally, so in Bandit optimization is this framework for making decisions in uncertain environments. So this can be formulated as a repeated game between a learner and an adversary. When I say adversary, okay, maybe let me come to adversary later. So the game goes on like this. So in each round, the learner chooses some action yt from the decision set x. And then there's an adversary who picks a loss function ft. And in this work, mostly ft is going to be some convex loss function, which is unknown to the learner. And the learner gets to see the loss ft evaluated at yt. So they just get to see the scalar loss. They don't get to see the entire loss function ft. And the adversary model that we study is, there are two kinds of models. One is the oblivious adversary model, where the sequence of loss functions ft that the adversary is choosing are chosen before the start of this game, before the beginning of this game. And there is an adaptive adversary which can actually look at the historical actions of the learner and pick an ft, which can make the loss, increase the loss for the learner. Okay, so the goal of this in this problem is to minimize the cumulative loss that the learner suffers over time. And the baseline that we compare against this loss is something called, is nothing but the minimizer of this cumulative loss across all the time steps. And regret measures how far away are we from this optimal point. Yeah, it should be, there should be a summation here. I think it's missing. Yeah, that's a good point. Yeah, if you just minimize for every t, I don't think it's possible to do anything there. Okay, so this problem has been well studied. So for example, probably many of you might have heard of multi-arm bandits. So this is a special case of that problem. So multi-arm bandits is a special case of this when x is a probability simplex and ft is a linear loss function. And there are many well-known algorithms which achieve the optimal regret bounds in that setting. But we are primarily interested in a more general setting where ft is a general convex loss function. Okay, so why are we even interested in this problem? So one of the classical applications of bandits and online learning is to solve two-player games. So in general, the goal in two-player games is you want to find Nash equilibrium of this. It may not always exist, but if G is convex concave, it's reasonably, you can show under some conditions it exists. But anyway, so to find the Nash equilibrium of this game, what we can do is we can make the X player and the Y player play two regret minimization algorithms. And then we can show that over time, both the algorithms start producing iterates which are close to the Nash equilibrium. Yes. So what? So maybe I can write this down just to be clear. So let's say time step t, you have these iterates xt, yt. So what the X player does is to produce xt plus 1, it just runs a no regret algorithm. Let's call it AX. So what I mean is it looks at the actions taken by the Y player would be the loss functions that this regret player, the X player looks at. Yeah, so the algorithm would take these inputs, the losses generated by the Y player, and then you just run this no regret algorithm and both the players do this, run two separate algorithms. Yeah. So these are your FTs. FT for the X would be this. and ft for the y player would be this. And yeah, you can show if you run this algorithm, the average iterates. You can show that these average iterates converge to the Nash equilibrium in terms of function values. Yeah, so moving along, yeah, these kind of min-max problems arise in a lot of cases. Probably a lot of you might be familiar with constraint optimization. So in constraint optimization, what you typically do is you write the Lagrangian formulation of this constraint problem, and then you get this min-max schemes. And often the Bandit algorithms that we design can solve such constraint optimization problems well. And they also arise in robust machine learning settings. So there are some more modern applications of bandits. So probably one area which recently picked up in the sense where bandit algorithms have recently started entering is online advertising. So here, when a user issues a query on search engines like Google, there will be advertisers who want to show ads to the users. So what happens is Google runs an auction for the advertisers, and whoever bids the highest or second highest, they get to show the ad. And when they show the ad, the reward they get is if a user clicks ad, then you get some reward for that. So it's a bandit setting because you only get to know the reward if you actually win the auction. And your action space is a set of all bits. So your goal is to find the best bid that you can play to maximize your rewards. And recently, there were a lot of online bandit algorithms which have been applied to solve this problem. And and some other examples are hyperparameter optimization in machine learning. This is strictly not an adversarial setting. This is somewhat like a stochastic setting where FTs are just stochastic. But still, the algorithms in adversarial setting can still be used to solve this problem. And finally, there is also application for control, non-stochastic control, which I'll probably talk towards the end of my talk if I have time. Okay, so now let me try to describe what has been done for this problem. So early works in this have mostly looked at something called gradient-based methods. What I mean by that is, so you try to, let's say you're at time step t, you try to estimate the gradient of ft and then try to descend along that direction. But of course, you only have a single point feedback. So how do you estimate the gradient is a question. So what we do is, we can't directly estimate the gradient of ft, but instead we try to smooth it a little bit and then try to estimate it. So the exact smoothing we do is this. So we look at this v is some random vector drawn from the surface of a sphere, and you try to take this smooth function and try to estimate its gradient. And it turns out the gradient of this smooth function is nothing but this, where you just need a single point estimation evaluation of the function at x plus delta u. So now once you estimate this stochastic gradient or unbiased estimate of the gradient of this, all you need to do is just perform stochastic gradient descent on this smooth function. And this problem is well known. We do know that stochastic gradient descent on smooth functions converges very fast, and we in fact know it has this 1 over square root t style convergence rates. So the problem really boils down to how do you do this gradient estimation better? That's the only, or how do you do this? How to find the right smoothing for f, and how do you do this gradient estimation? And so there are a lot of works on this, but I'll highlight the four probably the important works here. So I think Flaxman and Kalai had this original work on this, where they showed that this simple gradient descent method can achieve t power 5 by 6 rates for bounded convex problems. These rates were later improved for specific classes of subclasses of problems. So for example, for linear settings, Jacob Abernethy had order square root regret, which is known to be optimal, because we do know in the full information setting, this is optimal rates. And for smooth convex and strongly convex, again, these works have studied this algorithm and showed that in the smooth convex case, you get t power 2/3, and strongly convex, you get t power half. But the moral of the story is just there are only two classes of problems for which we know that gradient-based methods give optimal rates, the square root t rates, and that is just linear and strongly convex and smooth. For a long time, people have tried to see whether can we improve these algorithms further to get optimal rates for general classes of problems. So recently, a few years back, Vivek had a work which achieves square root t regret, which is optimal in T for all bounded convex problems. The algorithm is based on continuous exponential weights algorithm. To be even more precise, I think they used some kernels merged with exponential weights. But the main issue of this algorithm is it's almost impractical to implement because its runtime, every iteration is very high polynomial in terms of the dimension and the time steps. So it's not a practical algorithm. And also Tor Latimore had one more work in 2020 which improves the rates of Sebastian Vivek even further and achieves even tighter bounds. But again, this is more information theoretic algorithm than an actual algorithm. So the goal of our work is really to see if we can get any regret optimal algorithms and at the same time be computationally efficient for general convex problems. So that's our bigger goal here. Okay, so what's the key idea that we have in this work? So if you remember the gradient descent algorithm that I just described, what it does is it tries to estimate the gradient at a point x. It tries to perturb, do some exploration around x, and tries to estimate the gradient from that 1-point feedback. So what happens is this kind of naive exploration, which gives which gives equal likelihood to every direction, is very bad. Just to give you an example here, these are all gradient-based methods that were developed in the past. We just plotted how the regret of this method scales when you try to, when the loss functions are quadratic. And you can see they're actually scaling as t power 2/3. The main reason for this is if you don't take the curvature into account and try to treat each direction equally, you will end up paying a lot more penalty along directions with high curvature. In the sense, let's take a very simple function. Let's say f of x is x squared. So if you just naively perturb this x and then try to query this f at this x plus delta u, then you can see the expected value of this after the perturbation is nothing but x squared plus delta square. So if delta is some constant, you are incurring a constant loss at every time step by perturbing along this direction. Whereas if x is just linear, expected value of x. So you don't have much, I mean, you won't pay any penalty in expectation, even if you explore by a large amount. Whereas if it's quadratic, you start paying this constant penalty if you explore a lot. So that's a key insight. Can we somehow do less exploration along high curvature directions and try to perform more exploration along low curvature directions? And in our work, we try to address this by trying to estimate the Hessians of the loss functions. Yeah.
So here, when you want to estimate, you draw these arms like multiple times.
It's 1-point. It's 1-point feedback. So you can only query the loss function once. Was that clear? No, just f of t evaluated at xt. Yeah, so in the tth iteration, you try to estimate the gradient of ft by querying it. So let's say at each, at each step, you're, let's say, at current iterate xt, and the adversary has some loss function ft, which is unknown to you. And your goal is to estimate ft of xt somehow. I mean, this is hard to estimate, but what I'm saying is what you can instead estimate is get some stochastic estimate of a smooth function, a smooth approximation of f. F twiddle t is the stochastic approximation. This one. And you only need the 1 point feedback for that. You can just use this as your estimate for the gradient.
But for this also you'd need to make another query, right?
Why do I need to make? In the sense, you just need to query at x plus delta u.
Yes, but how do you make this query?
So in the sense, that's the arm you play at that time step t.
But then you'd have moved to the next round, right? You played another.
No, but this is something you do at before the beginning of the round and then query at that round.
There is some querying also allowed. Is that the point? Maybe I can talk to you later.
So, I mean, by query in the sense, you can give one arm to the adversary, and the adversary will reveal the loss at that arm. And the arm that I'm going to choose is this at that time step t.
But the adversary is not constrained to again reveal the same loss to you, right? He can then.
I mean, within that round.
Oh, I see. Within a same round, you can query multiple.
No, there is only one I will query. This is the only query I will issue.
Oh, okay, I see. Oh, okay, okay.
There's no other query that we are issuing.
Okay.
Yeah, each FT is very different.
Yeah, so if each FT is very different, how is it useful to estimate the gradient of one guy?
So this is an interesting question. So what happens is you don't need to be optimal at every step. Like you don't need to minimize every FT. All you need to make sure is you minimize the cumulative loss. So even if you lag behind one time step in the cumulative loss, it won't change your entire loss too much. So your goal is to minimize this. Sorry, there should be a summation here across T. Your goal is to minimize the cumulative loss, not individual losses.
Wait, okay, where's the summation here? Is it before the min or after the min?
It's after the min. I mean, it should be inside here. That
I see. So you want to pick the same x for all t, not for all t minimize.
Same x for all the.
I see. I see.
So Arun, I guess you're saying, basically you're trying to capture some real world problems where at xt you can evaluate maybe a noisy gradient of ft xt. Right? But you can also maybe get the value of ft xt at that time. And I guess you're probably going to get some second order values as well, some noisy versions of that as well.
Sorry, so you are saying can we get FT evaluated at XT as well, or?
Yeah, I mean that, and maybe I guess you're probably going to also look at some kind of second derivative at XT.
Yes, we will try to estimate the second derivative at XT as well.
I see, and then.
But if you have the advantage of querying the same FT at 2 points, I think that will help much more. The issue is here we can only query once. But if you have the advantage of querying twice, that will reduce your noise in your estimates quite a lot.
So there are very clear applications where you can only query once and not twice.
Yeah, like this online bidding example that I mentioned, you only get to play the bid once and see the value. I mean, and then you'll move to the next query after that.
Right.
Making you repeat this thing. So ideal algorithm, I understand why you would prefer low curvature direction, but I don't quite understand after smoothing and taking the gradient of that smooth function, why would that lead to high curvature directions?
So the issue is once you smooth it, you're moving away from your true function, right? And you want to minimize the distance between the smooth function and your true function. And if you don't take the curvature into account, your smooth function can stay quite far from your true function. And you might end up optimizing a different loss compared to the actual loss. And it's easy to see, like for quadratics, you will end up paying quite a bit. So the key thing is how do you identify the right smoothing to do? And we are saying that the key insight we have is you need to make use of the Hessian information to really make the smooth function stay close to the actual function. Okay, so yeah, that's a key insight. So now let me try to explain the result that we have. So first of all, our result only applies to certain subclass of convex functions, which we call kappa convex functions. So let me first explain what these are. These are functions which have second order derivatives defined, and then the derivatives are bounded between, and there are some constants C1, C2, and a positive semi-definite matrix H, such that the Hessian evaluated at any x lies between these C1H and C2H. So the important thing is this H need not be full rank. So if it's full rank, then this is just a strongly convex function, but H could be low rank as well. Like for example, for generalized linear models like logistic regression, the Hessian is usually just rank 1. So even if it is rank 1, we are fine. So we just need the Hessian to be like constant multiples away from this H. Yeah, they're saying linear functions lie in this class because for linear functions, the second derivative is just 0 and this is trivially satisfied. And the quadratic, homogeneous quadratics also lie in this function class. And we also have strongly convex and smooth. And there are some exp concave loss functions. We can also show that they lie in this set of functions. Yeah. So here is our main result. So what we have is, suppose the sequence of loss functions chosen by the adversary are kappa convex. And by the way, that H can vary with T. H need not be fixed across all the iterations. And let's say the adversary is oblivious. Oblivious in the sense the set of loss functions it decides to play is decided before the start of the repeated game. Then we have this regret. Basically, the dependence on T is square root T, which is known to be optimal. And the dependence on D is a function of, think of it as like D power 3 times kappa for now. I think in D dependence, this is not exactly optimal. There are lower bounds. The best known lower bounds are D power 1.5, I think. We are slightly off in that. But other than that, yeah, we are optimal in T. And this result only holds in expectation. So what, later in the talk, I will also show how to extend, how this result can be extended to more general adaptive adversaries, where the adversary can actually look at your past actions and modify their loss functions, and also see how we can give high probability bounds later on. Okay, so there are a few remarks. One is, I will explain the algorithm, but the algorithm is at a high level just doing Bandit-Newton method. The algorithm is improper in the sense it can choose actions outside of your constraint set. Again, this I'll say how we can fix this later on. And the other interesting result is we have some corollaries for Bandit logistic regression. So what this does is, probably everyone is familiar with classical logistic regression, where you had given independent data samples x comma y from some distribution, and your goal is to learn the best linear fit that minimizes the logistic loss. We study this in the adversarial setting, where at each round, the adversary can choose the data points x comma y adversarially. And then your goal is to find the best fit for all those data points chosen. And we achieve a regret bound of e power d times square root t. D is a diameter of your domain for the x. This problem was well studied, has been well studied in various settings, ranging from full information feedback, where you get to see the entire FT. That is, you get to see the actual x comma y at each round. And the best known result in the Bandit setting is this max of e power d comma square root t, but this was in the stochastic setting. This is not in the adversarial setting. We actually show results for the adversarial setting. Actually, this should be e power d, not e power 2d. And more interestingly, our computational time is just order of d square, because all we do is just estimate the Hessians and then do Bandit Newton step. So that makes it a bit computationally efficient. Okay, so before going forward, I just want to see if there are any questions. Yeah.
By definition of strong convexity and smoothness, do you also have if y, if x, this quadratic penalty? So can I give the same thing?
Sorry, I didn't understand the question.
So can I have alternate characterization similar to what we have for strong convexity?
So what's the characterization you have in?
So just using f gradients, let's say.
I see, I see. So you mean the gradient of
Function minus its linear approximation, the quadratic.
I see.
Can I prove some?
Maybe you could, right? What if you just try to, I mean, let's say this is one dimensional. Can you just try to integrate this between 2 points x1, x2? And then maybe, yeah, it might be, I mean, it seems possible, definitely. No, I'll say the algorithm. I just want to, before going into the details, I just want to give the main result so that you won't get lost in the details. Yeah. Okay, so here is the main algorithm we have. So let's say you are at some time step t. What we do is we first generate two random vectors, vt1, vt2 from the surface of the sphere. And then let's say the current iterate is xt. We try to perturb it a little bit. This is our exploration that we do. This AT is the cumulative Hessian estimate. I'll explain how this, I'll tell you how this can be estimated. But the key point is you base your exploration based on the cumulative Hessian. So let's say there is one direction where the cumulative Hessian is quite large, you try to explore less in that direction. Okay, now how do we estimate the Hessians in the first place? So this is the gradient estimate, which is probably what you have already seen in the previous slides. Basically, you just query ft at yt, and then you get this estimate, which is known to be unbiased for the smooth loss. So what we do with Hessian estimation is we repeat this trick of 1-point gradient estimation again on that. We apply it again on the gradient. So that's why you will have these two terms coming up, VT1, VT2 transpose, and so on. This is just Stokes' theorem applied twice, and you can show that this will be your unbiased Hessian estimate for the loss. Yeah, once you have this estimate, you can compute your cumulative estimate, cumulative Hessian estimates just by adding this up. Eta is your learning rate, which we'll set later on. Okay, so once you have your gradient and Hessian estimates, what you do is you just do your standard Newton step. So you multiply the gradient with the inverse of the Hessian, and then you project it onto the domain. So this will be your xt plus 1. And then, yeah, you continue this process.
The question is, you're right that the average of this quantity over the unit sphere gives you the Hessian. Same for the gradient, but there's also a variance of this quantity. And is the variance as large as the expectation value itself? Like, why is the variance small?
So yeah, the variance, that's a good question. So for expectation analysis, okay, the first result I mentioned here is in expectation. So for that, you don't need to bound the variance. But in high probability results, we do need to bound the variance. I will tell you, yeah, the variance can blow up. I will tell you cases where it can blow up. And we have ways to handle it. It may not look neat, but yeah. Okay, so one thing to observe is the compute time of this algorithm is mostly dominated by this inversion, matrix inversion, which you can do in order d square. It's not d cube because if you see AT has a special structure where it can be written as sum of rank 1 matrices. and you can use some efficient ways to do this inversion iteratively. Yeah, so that's one step. And the other thing is this is improper in the sense the YT can go outside of your domain. So we always ensure XT is in the domain because of this projection step that we have. But YT can go out of the domain. So that's why we call it improper. And again, there are standard tricks to make it a proper learning algorithm. So we can use self-concordant barriers and other things. Again, I will try to go over them later in the talk. Okay, so let me now just give you some key steps in the proof. Like how does one prove this result?
Arun, can you give some intuition why you took 2 random directions on the sphere? Why not 1? Why not 3? Yeah.
So I can give you the idea behind how we arrived at that.
Mm-hmm.
So all we did was we took this gradient and we
Mhm.
applied the same theorem again, the Stokes theorem again on this. So that's why you get 2 different random vectors. Is that clear?
Yeah.
Yeah.
I mean, I guess the main thing is that you kind of don't want to follow the leader because then you become predictable. So you randomize a little bit so that you're not predictable. And this randomization is happening through these directions on the sphere, right?
So randomization is purely to estimate the gradients. So for example, the first point you raised, follow the leader. You mean, sorry, follow the leader is optimal, right? In the sense, if you know, by follow the leader, you mean you don't want to descend directly along FT. Is that what you mean?
Right. I mean, there's kind of a current best X, right? That would minimize the regrets so far.
Yeah.
I mean, that's what you're competing with.
Yes.
But if you compete with that, then your adversary knows that you're competing with that, and it will give noise in the away from there. So you want to kind of fool the adversary with some noisiness.
No, I would say noise is just the reason why we are adding this noise is purely for an estimating the gradient.
I see.
But the point that you are raising will exist even in the full information setting. In the sense, you don't want to blindly follow the
Right.
past loss function. Just try to blindly minimize the previous loss functions. You would want to have a good balance between that and stability.
I mean, just one point, if it might help answer Sandeep's question, is here we are doing gradient descent. So that's follow the regularized leader. So we're not doing follow the leader. It is already follow the regularized leader. So that already accounts for the stability issue. And
I see.
Randomness is only for...
Yeah, that's a good point. Yeah, all I'm saying is this noise is just to estimate the gradient, but we do have the follow the regularized leader through regularization. Okay, so there are just 2 key steps in the proof. The first is we show that this cumulative Hessian estimate concentrates well around the true cumulative Hessians. And this is something a straightforward proof in the sense standard concentration results. So I'm not going to go into this. But assuming we have this result, the next key step is you first of all break this regret into 2 terms. One is the regret with respect to the smooth function f2 Yeah. Yeah. One side is the recursive one, the other side is the random variable. What does the equality mean when you return the column? This one. There is no randomness on one side. Gradient is with respect to x. This is gradient with respect to x. Yeah. The other side has random variable. Is there an expectation of y or? No, this is integral over u. The randomness. U is u is uniformly sampled from the surface of a. Yeah, this is just the expectation written in a integral format. Yeah. 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 Sorry for the confusion. Yeah. Okay, so the next key step is we just divide this, break down this regret into two terms. One is regret with respect to the smooth function, and the other is how close your smooth function is to the true function. This step, you can actually just simply rely on the regret of online stochastic Newton method, which we know has good regret guarantees, like square root regret guarantees, and there is nothing new there. And this term, the closeness term, is where our exploration comes in the sense we show that this term actually, if you have strongly convex function, this actually goes down as 1 over square root t at each step. So if you sum over t steps, you get square root regret. Yeah, this just says whatever I described. So the first term is nothing but reduction to online stochastic Newton method. The second term is closeness of ft, f2. Okay, so this is the bound in expectation. But before I go into high probability bounds, I just want to see if there are any questions still now. Yeah. Yes, eta is the learning rate. So eta has to be set like, I think 1 over root t or something like that.
That's just measuring how much curvature you have at that point, and based on that, you'd take a smaller delta. I see.
So we have this identity added here, and given that we have convex functions, the cumulative Hessian is always invertible because these are positive semi-definite. You are right, we are doing a stochastic estimate of the Hessian, so there's no guarantee, but we do actually show that the Hessian is cumulative Hessian is invertible. I mean, it's slightly non-trivial, but you can show it using some martingale concentration inequalities. With high probability, it's true on, yeah. Yeah, with high probability, it's true. Okay, so yeah, sorry.
Explain the high probability, right? Because this unit sphere estimate somehow to me seems very counterintuitive. It seems to be with low probability you'll get the right answer, but you're saying it's with high probability.
You mean the concentration?
No. I mean even the unit sphere estimate of the Hessian. I see clearly in the expectation it gives the right answer, but somehow it seems to me. I mean, this is the same question I asked earlier.
You can have high variance. I totally agree. Yeah. 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 The variance scales. The variance can scale quite a lot, and it can also scale with t also because you have cumulative Hessians there.
And when you're trying to invert the Hessian, that can be additionally problematic, right? Because you need to, when you're trying to invert the Hessian, you're at a point where the Hessian is almost going to vanish, you could be in trouble.
No, we are always inverting only cumulative Hessians, and we have this identity array.
Nice.
So I don't think that way it will be harder.
Okay, thank you. But you'll explain the probability a little bit more later. Okay, thank you.
Yeah, so, okay, getting to the high probability bounds, I'll just give the high level ideas, but maybe we could discuss offline if you need more details. So you're right that FT that we are estimating, the local quadratic approximation. See, yeah, in Newton method, all we are doing is just approximating FT with this local quadratic approximation. And this can have high variance if you try to move far away from your point of estimate. And in fact, if your cumulative Hessian is scaling with t, this variance can scale with t also. So what's the idea here? How do we reduce the variance? So what we do is we restrict the learner, action space of the learner, to be always in this low variance regime. Like this gamma is some constant for now, it's order of one quantity. We always make sure we play actions only in these focus regions. These are called focus regions. And once you ensure this quantity is constant, you can show that the variance also doesn't blow. Yeah, AT has an I additive. It's, yeah, it's full rank. Yeah. So, is there a question? No, I'm saying we'll restrict the, this is a restriction we will add to the algorithm. Oh, this is not independent of D. Sorry, it's a quantity dependent on D. Yeah. It can be like 1 over D or something like that. I'm not bringing in D exactly because we're trying to be optimal in T here. But there will be D dependence on gamma. Okay, so yeah, this focus regions essentially just make sure you're always in this low variance estimate regions of your estimates. But there is a problem. Okay, let's say we continue working with these focus regions. All we can show is we have low regret with respect to the focus regions, not with respect to the entire domain. So that's a big problem. So what we do is we bring in a test which makes sure which checks whether the optimizer of your cumulative loss is going out of your focus region. And once it starts going out of your focus region, we try to stop the algorithm and restart it. In the sense, we just break it there and then we start fresh from that next iterate. So what's the key, what's the test that we have? The test is simply this. You look at your cumulative loss. These are F hat S is quadratic approximations that you have here. And you just try to check if this quantity is positive or negative. I mean, this is a small negative quantity, but roughly what we are saying is if this is positive, you just try to continue the algorithm. If it is negative, you stop the algorithm and then restart it. So what's the intuition here? So let's say until now, this quantity turned out to be positive. So what this means is, sorry, yeah, let's say at time step t this turned out to be negative. What we show is that it means the minimizer, the adversary is trying to push your minimizer out of this focus region. That's when you actually start having negative regret. Because you are trying to optimize for some actions in this FT and slowly the adversary is trying to go out of this focus region. So then we can show that you will actually start having negative regret at some point when the adversary tries to make the transition. And then we stop the algorithm if this happens.
How do you calculate the cumulative minimum over that focused region? Is it through
these F hat
convex?
No, this F hat S is something we know. These are quadratic.
Oh, okay, okay. I see.
These are local quadratic approximations that we made.
I see.
And then you just try to minimize this over this. FTs are convex sets, like intersection of ellipsoids. You can just No, we don't have access. F hat S are the estimates of the loss functions. These are quadratic approximations around YT, XT. Yeah, I'm not going into the details of these steps, but just to give you a high-level idea, this is what we do. So what we show, this is another result is for convex quadratics, we can show that this algorithm gets square root regret, but the dependence in D is quite bad here. But this result was later improved in a recent work by Tor, Lettimore and others, where they tried to use similar ideas, but they extended it to general, not just convex quadratics, but general convex functions. And they managed to get D power, I think, 2.5 times square root T. They also have a refined version of these focus regions and other things. Okay, so yeah, this result holds with high probability, and this also works for adaptive adversaries. In the sense, adversaries can actually look at the past actions and try to adapt based on that. Yeah, so before going into the control, I just want to see if there are any other questions.
Arun, can you just intuitively tell us that how would the strategy change when you're dealing with an oblivious adversary vis-a-vis adaptive adversary? What does one do differently?
So I guess that's something dependent on the algorithm also. So for example, yeah, actually, I don't have a good answer to that question. Sorry. I think I never thought through that question properly. But it's possible the same technique might work out for adaptive. I don't think we used anything specific for adaptive adversaries here. So it's possible whatever we did for oblivious can also work for adaptive adversaries. If you can just get that high probability bounds.
Okay.
That's the oblivious adversary. The adaptive adversaries can choose FTs after you play based on the past actions that you see.
So, but in the adaptive case, here your algorithm is trying to go towards low curvature regions, roughly speaking.
Yeah.
But if I know where you are and I know your estimates, let's say I also observe that, then I can always define one more function where I could suddenly boost the curvature around that region and try to play spoil sport, right? So somehow this still is sort of.
So what you mean? You try to increase curvature along some directions?
Because I have the other FT with me,
Yeah.
so I can. But I know that it's a sum of functions. Beyond a point, I cannot have too much effect. But it's adversarial, so I guess you can.
You can do it, but I'm just trying to understand.
Or maybe your kappa convex will force my thing not to bend too much. Is that?
No, this is. I think this strategy tolerate more. It works for general convex functions also.
Oh, okay, I see.
But your question, I think, it's not yet clear to me why that would be adversarial. In the sense, if you try to add curvature, in some sense, it's okay to me. Maybe it's just that your function will try to adapt to that curvature over time. I mean, the adversary can't make you move too much in one iteration anyway. So slowly it can adapt to that curvature maybe.
I see. Okay.
So, okay, I think I only have 5 minutes. So I'll just try to quickly explain the result. I may not go into the details of this. So one application of this result is to non-stochastic control. So in control, what you have is this system, which there is this underlying state xt, which evolves using based on this linear equations. A and B are some unknown system dynamics. UT is a control action, your controller, that your action that you play, that can change the evolution of the system. And WT is some perturbation. It could be random, it could be adversarial. And you only get to see, you don't get to see xt, you only get to see a linear transformation of xt, which is yt. So in some sense, the xt is hidden, all you can see is this noisy observations. And at every round t, you play a control ut, you take some action ut, and based on the state that the system goes to yt, you get some cost, ct of yt comma ut. And this ct is, again, it could be adversarially chosen, but we assume in this work it's convex. And the goal is to minimize this regret over time. So this is, again, is a cumulative loss you suffered over t steps, and this is the best policy in some policy class pi. So a few assumptions that we need in general when we are working with control is, we first of all need the system to be stable, in the sense, let's say if the norm of these matrices is quite large, the system can become unstable, in the sense the xt's can blow up over time. So in general, the system won't be stable if you don't have any assumptions on A and B. So we need some stability assumptions. I'm not going into the details, but roughly the stability assumptions would say something like the norm of A and norm of B should be quite small for the system to be stable. And we assume the perturbations WT and ET, that can be added to these observations and system XTs. They are generated by an oblivious adversary. And we also assume the quadratic costs are strongly convex and smooth. So these CTs are strongly convex and smooth. Okay, so what's known about this problem? So in the past, this work, first of all, the control problem has been really well studied in the literature, and most of the works usually study this under the stochastic noise. And either that or they assume full information setting. So in this work, we are just, we want to understand if we can give good control algorithms under the Bandit feedback setting. So that is, you only get to see this cost function. And then under adversarial perturbations, WT and UT are adversarial. Okay, so the first thing I need to explain is what is your comparator class, the policy class in this regret. We use something that is standard in the literature, which is called disturbance response controller class. This is a quite broad class of policies, and it captures a lot of important policies. Essentially, what it does is your control UT that you play is just a linear function of the past disturbances, WS and DS. I mean, the linear combination factors itself could be quite complex, but these are just linear functions of your WS and ES. And our goal is to optimal these find these optimal linear combinations M. Okay, so I'll just tell you the high-level idea. What is it that we do here? First of all, the key observation is since the system is stable, we can show that the effect of past actions decays over time. In the sense, what matters to you most is just the past M actions or so, and everything else will have very minimal effect. That's one observation. And based on that, what we do is we reduce this control problem to Bandit optimization with memory. What do I mean by that? Just abstracting out, in Bandit optimization with memory, you have a loss function ft, which the adversary can choose at time step t. But the loss itself can depend on all your past M actions. It's not just your most recent action, but all the past M actions affect your loss. And what we show in this work is you can reduce a control problem to this problem, Bandit convex optimization with memory, for a reasonable choice of M. And then our goal is to minimize the regret of this Bandit optimization with memory. Okay. Yeah, you can ignore this, but let me go to the main result. So what we have is that assuming the system is stable and the costs are strongly convex and smooth, and our noises are generated by an oblivious adversary, we show that the Bandit Newton step that I just described can also solve this Bandit optimization with memory problem and still give you the square root regret. But of course, the added challenge here is you have this dependence on all the M past actions, and we need to control for that. But yeah, given the lack of time, I'm not going into that. But basically, the ideas from Bandit Newton method carry over to this, and you can show that you get the square root regret. Okay, so just concluding, the main point in this talk is you need the right exploration or the right smoothing to be done to get the optimal regret in Bandit optimization. And we propose this Bandit Newton step for kappa convex losses. So the algorithm relies on this Hessian estimate from single point feedback. And we also showed techniques for converting this problem into high probability guarantees. And then in terms of future work, I think these are mostly already done in the sense there was one recent work by Todd Latimore which extended these algorithms to general convex functions and made it also a proper algorithm. But I think there are still some open questions in non-stochastic control. In general, how would you consider general cost functions and still get square root regret is still an open question. Yeah. So that's all I have.
So this BNS algorithm is optimal in T, right?
It's T.
But in D, is there a matching lower bound, or is the lower bound known?
First of all, in Bandit setting, it's not even clear what's the optimal dependence in D. The best known lower bounds as of now are D power 1.5. The best known upper bounds are D power 2.5. It's an algorithm recently by Todd Latimore, which relies on Bandit Newton step that we have, but it adds a few things on top and gets D power 2.5. It's not clear whether which one is the tighter one or which one is the looser one.